Okay, so we left off talking about how pH is a measure of how acidic or basic a solution is. And this ranges from 0 to 14. So some examples of this would be battery acid is super acidic, right? Its pH is basically 0. Your stomach acid or like lemon juice, vinegar and soda, those have a pH around 2 or 3 typically. Closer to neutral land, we have milk and human blood. Seawater is usually a little bit basic, around 8.1. And then as you start to get into like household cleaners, like ammonia or bleach, those are very basic. And so those are down in the like 11 to 13 range. So that gives you maybe a little bit of an idea about how this pH scale works. And so if the pH is less than 7, then there's more acidic things, the H pluses, than there are basic things, the OH minus. Oh gosh, I don't know what just happened. Anyway, pH equal to 7 means that H plus equals OH minus. And pH bigger than 7 means there's more H pluses than OH minuses. Just kidding, I said that backwards. If it's greater than 7, there's less H pluses than OH minuses. The pH of pure water is 7. So if you have water without anything else in it, its pH is 7. And the acceptable drinking range for water is between 6.5 and 8.5. It's okay if your water is a little bit acidic. It's okay if it's a little bit basic, but you don't really want to stray too far outside of that range. It can start to freak your body out a little bit, which is, typically a good thing to avoid. Don't freak out your body. Contamination in drinking water is a serious concern, and so we have an organization called the EPA, the Environmental Protection Agency, and they monitor the content of our drinking water. They also monitor a lot of the freshwater sources and the ocean and water throughout the country to make sure it's in good shape. Not always convinced that they're doing a great job of that, but at least somebody's out there trying. They also set some standards to protect public health by limiting the levels of contaminants in drinking water. And ideally, these standards are met. There are a lot of instances where they're not met, and that's a serious concern in our nation and around the world. So some things that the EPA limits include microorganisms, so like little bacteria and parasites and dudes like that. They try to limit disinfectants. You don't want to consume disinfectants. It doesn't have the desired effect. It will make you sick or kill you instead. Disinfection byproducts are not allowed in the EPA, so these are chemicals that result after cleaning something. And then inorganic chemicals are typically not allowed as well. Organic chemicals are something we look for also, and we just want to make sure that anything harmful really stays out of our water. Obviously, radionuclides, which is just a fancy way of saying radioactive stuff, clearly don't want radioactive stuff in our water. There's a link here to the EPA website, and it talks about our regulated drinking water contaminants if you're interested in more of those details. So the reason solubility becomes so important is that humans and all living things depend on fresh water. Right? We depend on the water that's around us that's not salty, and it doesn't have a bunch of crap dissolved in it, so it's safe for us to drink. When nasty stuff gets into our fresh water, we have a problem because it's often soluble in the fresh water, and so then we don't necessarily even know that it's in there. Like the dude in this picture is drinking some water that looks really dirty, but even when water looks clean, sometimes it has stuff dissolved in it that makes it not good to drink, right? If you dissolve salt in water, you can't tell the salt's in there, but if you try to drink it, you'll figure out pretty quickly that there's salt in there. Most of our fresh water is on the surface of the earth, and it's stored in like glaciers and lakes and rivers and ice caps, and we'll get into that. But the rest of our fresh water is what we call groundwater, and this is a lot of the water that we use. Groundwater is just a term we use for water that's stored in the ground. Go figure, it kind of sounds like exactly what it is. So this image shows some different pieces of the water cycle. Importantly, we can see the groundwater because we have this cross section. So groundwater is represented by blue, and then this brown part is dirt and soil and rocks that do not contain water. So sometimes the water reaches the surface of the earth, but a lot of times we have to reach down to get to that water. And sometimes there's other things that we want down there as well. So we have the water that's beneath the ground. You can see when we drill wells down, that also creates opportunities. Even though we're getting water out, it can create some opportunities for water to go in as well. So when you irrigate agriculture, any fertilizer you use can eventually make its way into the water table. Anything that ends up in this river, right, that can end up in the water table down here where the groundwater is. The water treatment plant sometimes returns water into the groundwater. And so there's a lot of different things kind of coming in and out of our groundwater at any time. And we want to make sure that those are things that are safe and healthy for us and for the wildlife and the living things and plants and stuff. So what we want to think about is, how do pollutants, so how does stuff that's dissolved in water move in this water table? Like if something gets in the groundwater, does it stay there? Can it come out of the water? Like could it end up over here in the well supply? Or could it end up somehow in our wildlife refuge? Those are the things that we want to think about. And so to do that, we're going to do a lab. This is called the Groundwater Lab. The purpose is to observe and follow the pollution near a river and underground. And you'll design an experiment to observe and follow a surface spill in a flat area. So kind of what happens if pollution gets underground somehow? Does it move around? And then what happens if we have some pollution that happens on the surface of the earth? Can that move around into the groundwater as well? The model that we're using is based on the fact that the ground is mostly rock with a thin layer of topsoil. So I want to focus mostly on how the water moves through the rock to track how pollution moves through the ground. So we have 2 sheets of plexiglass that we're going to hold together with hardware, so like screw and nuts and bolts. And we're going to fill that with sand. And the sand is loose, but it represents the solid sandstone. Sandstone is a really typical aquifer, and it has moderate porosity and is permeable. And that just means that water can flow through it. Because even though sandstone is a rock, water molecules are way, way tinier than the holes between the little pieces of sandstone. So this is a rough sketch over on the right of what your simulation is going to look like. You're going to have sand. You're going to use a little black foam spongy guy to make the shape of a riverbed. And then there's a hole in one of the pieces of plexiglass that simulates the river flow. So it allows the river to flow out, and that allows for water movement to happen. Notably, you want your hole up here in the sponge space, not down here where the sand is, or the sand will fall out the hole. Seems pretty obvious, but you would be surprised. Here's a picture of what this looks like in real life. Here is the sand and the setup with the plexiglass and the rubber tube that holds the sand in. Here's somebody, starting to drip water into it to create the groundwater in the sand aquifer. So some implications of the model: the pore size of the sand is bigger than what's squished together in sandstone. So by making the pore size bigger, the water is going to travel faster. Otherwise, this would take for freaking ever. It takes groundwater weeks to move because it just moves like a centimeter per day. So that's why we're using sand instead of sandstone. Right? That would take forever. Ain't nobody got time for that. So to get ready for this lab, which we're going to do next week, you guys should read and annotate the whole lab. You will get a paper copy of this lab in class if you have not already. And so you are going to highlight wherever it asks you to make observations. You're going to highlight anywhere it asks you to make predictions. You are going to answer questions 1 through 6 and write the predictions. And then you're going to write down any questions you might have about the procedure, like how do we do this or why are we doing this way. So this will be due when you arrive in class next week. So that'll be Monday if you're A group, and it'll be Tuesday if you're B group. I'm really excited to do this lab with you guys. It's really fun to get a little messy and kind of see how the pollution can move with the water throughout the ground and an ecosystem. Okay, so that's all I got for you guys. Thanks for listening. I'll see y'all soon.